Nous allons accueillir maintenant Marwan ABDOU AHMED. Je vais me permettre une petite introduction pendant qu'il s'installe. Donc, en 2003, il a obtenu son doctorat à l'université de Saint-Étienne. Je crois que vous allez faire une présentation en français. En anglais. Ah, en anglais, ce sera en anglais. Donc, il a rejoint l'Allemagne tout de suite après, en 2004, pour l'université de Stuttgart et travaillé à l'Institut für Strahlwerkzeuge. Une notion d'allemand, c'est très loin. Et donc, en 2004, il s'est consacré principalement sur le développement de l'optique sélective en polarisation et en longueur d'onde pour les lasers à l'électrophonique de haute puissance. Depuis juin 2011, il dirige le département de cet institut et son équipe est spécialisée dans les systèmes laser à disque fin, ultra rapides et de haute puissance, ainsi que dans la mise en forme temporelle et spatiale du faisceau, et aussi pour l'optique de distribution de faisceaux par flux. Voilà, bien entendu, il a participé à plusieurs projets nationaux et européens qu'il a coordonnés. Nous avons vraiment la chance qu'il a accepté cette invitation. Je vous remercie pour votre écoute et je lui laisse la parole.
Merci. Merci Patricia. I will give my talk in English, as I have seen that some of the colleagues present here are not native French speakers. So my name is Marwan, as mentioned by Patricia. I'm coming from the IFSW. It's easier to pronounce than Institut für Strahlwerkzeuge, from the University of Stuttgart. And today I will just present kind of status on the thin disk laser technology and where it goes at present. So I will just present very briefly our institute. I mean, our approach, we develop laser sources for applications. And applications, I mean industrial applications, because we are talking about very high power lasers. But in some cases, we have also the needs from our application colleagues about specific sources that we develop for them. So it goes the two ways, actually, either from the laser source to the application or from the application to the laser source. For that, I mean, the institute is divided in three departments, I mean, that I can very briefly present here. We have process fundamentals. I mean, it's light matter interaction and understanding the physics of the processes. We have a system engineering department, which is dealing with artificial intelligence and optimization of processes, including some photonic systems produced by lasers for the quantum technologies. And the department that I am leading is developing lasers and optics. And in this department, we have three groups. Thin disk lasers, I mean, this will be the main topic of today, but we are also working a lot on beam shaping. I will show you some examples where we use some optics. I will just tend to say we are using resonant diffraction gratings that we use for our high power lasers. But also since 2004, we have an activity on fiber, but only fiber beam delivery optics. And over the last few years, we are focusing on hollow core fibers, from design to implementation and qualification using our femtosecond lasers. So as I said, I mean, high power lasers, the main application is material processing. I mean, it can go from cutting to micro machining, I mean, ablation processes, large area surface texturing. I mean, this is nowadays, as you know, very, I call it a hype, because it's required in many fields, in aeronautics, but also in the food industry and so on. And also high aspect ratio holes, which are drilled with the ultra-short pulsed lasers. This is mainly the main activities, but of course it's not only for metals, but for other different materials like ceramic or transparent materials. So the main challenges in power scaling of solid-state lasers is, as you know it, I mean, when you want to scale the average power, you have to manage the temperature effect, the thermal management. And if you want to scale the peak power, you need then to manage the nonlinear effects. I mean, for the nonlinear effect, I mean, you all know the Nobel Prize of 2018, I mean, you can implement CPA approaches where you stretch your pulses and then recompress them after amplifiers and so on. And here for the thermal management, most of the time you solve this problem with the geometry of your laser. And for that, since over the last decades, I mean, maybe the last 30 years, I mean, the lasers, I mean, the initial lasers were rod-type lasers where they suffered a lot from thermal issues and therefore brightness degradation and so on. So scaling the power was becoming very difficult. And over the last years, there are 3 technologies which have been developed, invented to circumvent this problem. The first one that has been invented at our institute in Stuttgart was the thin disk laser technology. This one I will then describe more in details, but you have also the slab and the fibers. The idea was just to increase the surface to volume of your laser active medium. That's basically the basic idea to manage your thermal issues. And for the thin disk, as I said, you just take your rod and you just flatten it, going to a few hundred micron. Therefore, you can increase, when you have a large pump spot, you can increase your surface to volume ratio. Since you are cooling from the backside, you can have a very efficient cooling and then heat extraction. Axial heat removal, this is important to minimize the thermal aberration, the thermally induced aberration, and therefore the thermal lengths. You can then pump at high pump power densities. The only issue that you have is, since you are going to very thin laser active medium, you need then to have an efficient pumping scheme. Therefore, you cannot make just a single pass with your pump light. So you need to develop a special, which I will show you a bit later, a special pumping optics to recirculate your pump radiation so that you can reach more than 90–95% of pump light absorption. And what is interesting with the thin disk is that if you want to scale the power, you just increase the size of your pump beam. And this is kind of easy to implement by just some simple optic design. So how a thin disk laser active medium look like? It's basically you have your laser active medium. I mean, typically for thin disk, the most advanced is ytterbium YAG or ytterbium LUAG materials with the thickness in the range of 100 to 300 micron, a doping concentration between 7 and 11%, which is on the front side AR coated for both pump wavelengths and signal wavelength, and on the back side it is HR coating for both wavelengths as well. What you have to keep in mind here is that we want to use the back cooling the disk from the back side. Therefore, we have this HR mirror, which is then lead to the fact that the thin disk is also used as one of the cavity mirrors of the resonator that you want to build up. So typically, then, of course, when you have your disk which is prepared, you have to mount it on your cooling finger, what we call our cooling device, where you have your impingement of the water from the backside. There are 2 ways of doing this. Either you are soldering the laser crystal on the heatsink, or you are gluing it on a diamond heatsink. This is an example of a soldered disk that we have been developing at our institute. But here you have an example of a disk. As you can see here, I think this one is 17 millimeter diameter, which was glued on the 20 millimeter diameter polycrystalline diamond. That's interesting because the best heat conductivity that you can achieve from a material is from a diamond. And then, of course, you have a lot of process that you mount your disk on the cooling finger and all these assemblies. All these parts are designed also in-house and assembled in-house. As I mentioned, the problem is that you have a very thin laser active medium, so the single pass absorption of the pump light is for few percent, so you cannot achieve an efficient laser process with this. What we do then is you have to implement a pumping scheme, which is basically composed of a parabolic mirror and retroreflector prism mirrors. When you inject your pump light, you first reflect on the parabolic mirror, then going to the disk, which send back to the parabolic mirror, and then going to the retroreflector, and then you can circulate like that your pump light until you achieve, depending on the parameter of your disk, sufficient pump light absorption. Typically, it's 24 passes of pump light reflection for a typical disc in the range of 200 micron and 7% of doping. But you can also go to very thinner with the higher dopings if you want. And at the same time, you can also increase the number of passes. There are some materials which have low absorption, low pump absorption, so they can benefit then from higher number of passes of the pump light. And as I said, going to thinner disc, you go also in the same direction in average power scaling, and then you can have a better heat extraction. That's how it works. It looks complicated, but at the end of the day, it's Lego-like. Believe me, within half an hour, you can assemble this and then align your pump optics and then just put it in your laser cavity. So now I will just come to the outline of my talk. After this introduction, I will very, very briefly present what has been developed lately on continuous wave thin disk lasers and nanosecond. For the continuous wave, there is not much of development. There is just power scaling, of course. But there is one aspect that I will present in more details. Then I will discuss also on ultra-fast thin disk lasers. And then we'll conclude with what's next. What do we do after this? So as I said, I mean, for CW infrared radiation, there is not much of a development beside of a lot of engineering. How can we extract more power from a single disk? This nowadays, you can buy a thin disk laser from the company Trump with 10 kilowatt per disk. That's possible. So the latest development was mainly going into using the thin disk laser to generate high power of green radiation in continuous wave. As we know, this is kind of difficult, and one of the advantages of the thin disk laser is that you have an extremely high intracavity power. So you can take benefit from that as one aspect to have an efficient conversion in your nonlinear crystal. The second point is, of course, you need to have very good crystals, and for that we are collaborating with the company Crystal Laser here in France. And an important aspect also for the efficient phase matching is to have a clean polarization of your fundamental wavelengths, but also a narrow bandwidth to have an efficient conversion efficiency. For that, we use resonant diffraction gratings, which are operating in the Litroff condition, and we design them. I mean, we developed the concept. We don't produce them, but we have partners who can do this for us, where we can achieve a very high diffraction efficiency in the minus first order, higher than 99.7%. Due to the fact that you have a dispersive element, you can then understand that you can have a very narrow select bandwidth of your infrared radiation by implementing such a device. This gives us, of course, in a multi-mode cavity, a bandwidth of 0.1 nanometer of the infrared radiation. Typically, it's in the range of 2 nanometers. And a very high degree of linear polarization. That's also very important for the phase matching. By doing so we could demonstrate more than 1 kilowatt continuous wave green radiation with a very high efficiency of 52% approximately. And by efficiency here is from the pump power to the green power. That's very huge. I mean, for the infrared, we were basically in the 65%. So, and this is because we have a very low loss component that we are using, but we have also very high quality crystals. I did not show the result here, but in another experiment, we could achieve more than 1.4 kilowatt with 55% of optical efficiency in this case. This attracted the attention, and nowadays you can buy also 2 kilowatt green CW green lasers, which are available on the market. Another interesting thing is that the thin disk laser, the fact that you have an anisotropic material and you have less effect on thermally induced aberration or birefringence, you can then also try to select some very specific modes like this do not shape, which can be also interesting for material processing. It has been reported that you can cut much faster with radially polarized beam. Here again, sub-wavelength grating implemented as a cavity and mirror to select this kind of mode from your resonator. And when you look to the polarization of this mode, you can just put an analyzer and then you can see that you will have the lobe just rotating according to the transmission axis of your analyzer. And the effect here is basically inducing thanks to the grating, different reflectivities between the two polarization states, and therefore you can dump one of the polarization and only oscillate this one. Here we could demonstrate 1 kilowatt, just limited by the pump power available at that time. Nanosecond, these are not our result. I just wanted to mention because Trump is very, very active with these high power nanosecond lasers. Q-switched in this case, where they could demonstrate 4 kilowatt in the lab or 20 nanoseconds. I will not spend more time because this is the work of the colleagues which have been presented. But it's important to show that it is also possible and it's very well adapted for this high energy, to work with thin disk laser for the generation of nanosecond pulses, in this case 20 nanosecond. They did the same also with green, conversion. In that case, it was an intra-cavity dumped resonator. And in the UV, they shown an impressive result of 1 kilowatt of UV. That was just, and the market behind it is, you can make educated guesses here. The idea is to take over what is done with excimer laser, of course. Now I will just switch to the ultra-fast thin disk lasers. Here I know that there are a lot of people who are developing crystals. We always look for good crystals. Here, just to give you an overview that the thin disk laser technology has been also demonstrated from the visible to the mid-IR with different dopant and different host materials. I just give an example here of the Presidium Strahlo that we have been demonstrating in-house. We have also very recently demonstrated an old crystal which was pulled at the site from the laser community, alexandrite. Alexandrite thin disk laser with approximately 15 watt titanium sapphire also. We made a demonstration within a European project. But most of the work was, of course, based on ytterbium doped materials which were lately pushed by several groups. Neodymium at different wavelengths, but also thulium and holmium doped materials have been also reported. In this case, it was a chromium zinc selenide thin disk laser. Now, if you look a bit more in details for the ytterbium doped materials, you have several. This is just CW multimode. There have been work demonstrating, as I said, 10 kilowatt from a single ytterbium yak disk by Trump company, and here is a Chinese group with Luag. What is interesting here, just as a message, is that you have some very interesting materials which have interesting spectroscopic behaviors, which can then lead in mode-locked oscillator to very short pulses. For example, calcium fluoride, the Cesky oxide materials like lutetium oxide. Here we have been demonstrating 1 kilowatt of average power with ceramic ytterbium lutetium oxide material. And you have the whole list with the references here. I will not go into the details, just to give you an idea that there have been a lot of work, there have been a lot of trials in also exploring other materials, exotic, we call them the exotic materials for this technology. And the same, of course, mode locking has been demonstrated with calcium fluoride in-house, Calgo together with Chimie Paris and Laboratoire Charles Fabry some years back, where we SSO, YAB as well, and lutetium oxide and Lusco by other group of Ursula Keller. Now I will focus on what we have been really focusing on over the last years is what we call the thin disk multipass amplifier. The idea to scale power, of ultra-short laser pulses, the most simple way is to use an amplifier. This you know it. From a single oscillator reaching the kilowatt or more, it can be challenging. So what we have done here is that we have the key, this is just a schematic of the setup. You have a seed laser You have your disk, which is pumped. We have been choosing here pumping at 969 nanometers and narrow bandwidth in the absorption line of ytterbium YAG. But you need, of course, stabilized diode for this. This was nowadays possible. The disk, of course, and an array of mirrors. And the idea is just to overlap geometrically the seed beam on your thin disk, which is pumped here. And by this, the number of passes through the disk is depending on the number of mirrors that you apply in your array. So by that, you can then start from, I don't know, 50 watt or 100 watt and scale to the, and now I will just present the latest result that we achieved using this concept. If you have a good student, it can then implement a very nice way of visualizing this. I mean, just, yeah, this is to show you the whole propagation of the seed beam through the disk. You have here mirror, which are changing just the height in your array. You have retroreflector mirrors here that we implemented to minimize the effect of the hot air wedge in front of the disk, so that you can then bring it back each time it goes in a passive way. And of course, there is a lot of engineering. And we are talking about kilowatt class power. The physics is known. It's just to make sure that your system is, and this is how it looks in the lab. Here is the array. Here is the module where the disk is implemented, the pumping module. And here you see the retroreflector mirrors. And of course, we had to package this for safety measures for the application later. So this is then a first example on high power picosecond laser that was using this approach of thin disk multipass amplifier. We started with the seed laser, what we call seed laser for us. It's a 100 watt class. It's not the milliwatt like in other systems. And we build up two stages amplifiers, multipass amplifiers. In the first stage, we could extract 435 watt, which was then boosted to 2 kilowatt afterwards. What's interesting here is that we started with a relatively good beam quality, and we have a slight degradation, but still at 2 kilowatt of average power, it's not that bad, I would say. We see some aberration. I mean, of course, the thin disk is known that you can reduce all what is thermally induced, but you can't completely cancel it. And with more than 2 kilowatt and an energy per pulse of nearly 7 millijoule in this experiment. Of course, when you have this high power infrared, you are interested also to see if you can go to the visible, and we have implemented then a stage where we have an LBO crystal. This is, as I said, a collaboration also with Crystal Laser to push the limit of also green radiation in the picosecond. And in that case, we crossed the 1.4 kilowatt of average output power with a very good efficiency and also good beam quality factor. In the same, not exactly the same setup, we were also conducting, I will not show them here, we were conducting also experiment for the UV, where we demonstrated 265 watt. So you can do the same before going to this, of course, I mean, this laser was developed for an application on texturing. And we wanted, of course, to implement this. And this is here, you can see, where we developed what is called a DLIP, direct laser interference patterning system. You have just, you split your beam and then interfere the two beams. And where one of the goals was to texture tubes, but also mold, which are used to fabricate the water tanks of dishwashers, what you have all in-house. The idea is, of course, to have antibacterial structures on these devices and to show, because of the high average power, to show very high productivity in the texturing. Just to illustrate this example, I mean, of course, then what is also interesting is what we demonstrated is that you can also amplify directly femtosecond pulses. Since you have a very thin laser active medium, the non-linearities are reduced when you compare it to fibers. You can push the limit, let's say, of amplifying femtosecond pulses directly. And here we use a commercial system, the Spirit 100 from the company Spectra Physics, with 100 watt, 260 femtosecond, the same scheme. Improved engineering, because we were not very happy with the beam quality we were obtaining with the other system. And we could extract more than 1 kilowatt and 1 millijoule of femtosecond pulses, sub 400 femtosecond in that case. As I said, we worked a lot on the engineering and minimizing some thermal issues in the whole amplifiers. And what was impressive to us, at least, is that we see a very, very small degradation of the beam quality factor between the seed beam and the beam that has been amplified to 1 kilowatt in this case. That was a big step also in the development of this multipass amplifier for us. The laser was meant, of course, for material processing. You cannot just develop a 1 kilowatt laser which works for 10 minutes. That's not acceptable. So you need to make sure that you have stable power, stable beam quality. And we had, of course, pushed by the partners to verify this. And we conducted long-term, it's not days, but at least a few hours, to show that we have a very low power fluctuation, we have a constant beam quality, and the behavior of the amplifier was kind of repeatable with switch on and switch off, how do you say, cycles, without any problem. The same also was done on another. I will not go into the details. Here we had different pulse characteristics, but the most important here is that we could go to higher energy than the previous setup. And in that case also we conducted second and third harmonic generation. That's just to illustrate that when you have a powerful IR, you also want to use, because there are some applications we can benefit from these wavelengths here. This is an example of application for this laser system that has been developed here together with Amplitude within the project, the European project HyperDias, where the objective was to demonstrate very high ablation efficiency or ablation rate of silicon. This was a challenge, and we had the partner Bosch as partner. And the important information from this slide is that the roughness of the texture of the ablated surface or sample were very small, and there was an increase in the ablation rate of the silicon. At that time, I don't know the latest result, but at that time it was more than 400 times the state-of-the-art result. So here's just a summary. I want also to just briefly say that within this kilowatt FlexiBurst project, I did not show the result, but you have heard it, I think, from several people that gigahertz burst is very beneficial for material processing. And we were also working on amplifying gigahertz burst to the kilowatt class in this case. Again, here, of course, there are some special modes. I add this slide because to show that it's easier to amplify custom design or customized mode in thin disk technology or thin disk geometry when you compare it to fibers, where you can have other issues like maintaining the polarization of that wood. We were also working extensively on amplifying beams with radial and azimuthal polarization, because it has been reported that you can drill much faster when you use azimuthally polarized beam in metals when you compare it to standard circular polarization. So the idea is to have a seed to implement a polarization converter, which gives you then from a Gaussian beam to a ring, radially polarized, and we amplify this in the same scheme. Of course, in that case, you have to be very, very careful with the optics that you are implementing, because this kind of polarization can be very sensitive to any phase shifting effect. You can then compensate for that. We conducted several experiments, and the latest one was for picosecond pulses, where we demonstrated 1.7 kilowatt of azimutally polarized beam. This was not in a single stage, it was in 2 stages amplifier. So just to now summarize where we are, I mean, this is just an overview of all report on high power ultra-fast lasers from the different technologies, fibers, slab, thin disk regen, thin disk multipass amplifier, but also mode lock thin disk oscillators that you can see here in green. Lately, the group of Ursula Keller have shown several hundred watt, 550 watt with a few millijoule. So the multipass amplifier results are here, but also at high energy. For example, it has been demonstrated close to the joule of pulse energy at 1 kilowatt of average power. You see the 10 kilowatt reported here. This is the coherently combined fiber amplifiers from Jena. And oops, so you can see also that there are several now commercially available devices which are based on the different technologies. I mean, this has been released recently. This is based on the thin disk multipass amplifier. I mean, Trump has released a 1 kilowatt, 10 millijoule, 1 picosecond laser system that you can buy today. So what's next now? I mean, as I said, increasing the average power is managing the thermal issues. I showed you a disk where we have an HR mirror, which is coated on the disk. This is known as a heat barrier. I mean, this, because of the heat conductivity, you can very badly extract the heat which is generated in the laser active medium. So we have now a new concept that we are following at present, which what we call the symmetrically cooled thin disk. Basically, the idea is that you have your laser active medium that you can see in red, which is sandwiched between transparent diamond heat sinks and mounted, as you can see here, through polycrystalline and water cooling. So we conducted first thermal simulation where we could see that we can extract the heat approximately 10 times or 9 times better than the standard configuration that I have showed you at the beginning of my presentation. So that's very promising. Of course, there are a lot of challenges to be solved. This is not the end of the story. How to mount this, how to assemble that. There is a lot of technological things to follow. And then the next is what we are in at the system-based. I mean, we are hearing nowadays that the application people want more flexibility, so they want to have access to different operation mode of the thin disk, of the laser, sorry. And if you look to the manufacturing process according to this DIN, all these processes can be done by laser. But today you have, for each of them, one laser and one machine which are different, I mean, from the other. But this will change, and this is our vision, is to have a single laser that can do everything. I mean, here is an example of an application, for example, where you can combine additive manufacturing plus subtractive manufacturing within one laser source. I mean, you can see here, you can just make your additive part and then shoot again with your pulse system so that you can drill very high aspect ratio structures. And for that, of course, you need the right laser. We want to avoid to have multiple lasers, and one of the platforms that we think is adapted for that is the thin disk multipass amplifier that I showed you. So this is then our goal to reach. I mean, this is what we have been demonstrating lately. One laser which can then allow us to do CW in a solo mode, when I want just a CW, pulsed for the drilling, but also both of them sequentially or simultaneously. We want to be fast, switching between the two, but we want also sufficient power to address the different processes. And we want to have also the flexibility in the ratio between the power and all, I mean, just to have arbitrarily all kind of radiation on the workpiece. This is what we have been implementing. For the demonstration, we have been using 2 different seeds. We multiplex them via polarization, and this is also one of the advantages of the thin disk is that you are polarization insensitive in terms of amplification as well. The amplifier is the thin disk multipass amplifier that I showed you earlier. We demultiplex them to be able then to modulate each of them separately, and then we multiplex them again on the workpiece. So this is just as a proof of concept. There are, of course, techniques which can allow to reduce the complexity of this. This is how it looks then in reality. We have a CW seed, 2 AOMs, which can then control the power that you inject in your amplifier separately. You have your polarization multiplexer here. One has a S and the other P polarization that you can combine in a common multipass amplifier, then demultiplex them with another TFP, modulate the power of each of them separately, and recombine them on the workpiece. So this gives you an additional degree of freedom to say, okay, I can then modulate how much power I have from my CW beam to my picosecond or femtosecond laser. This is what has been then implemented. You can, as I said, operate it in solo or in simultaneous. Just here the result to show that we achieved the 500 watt with a very good beam quality when we operate the system in solo or in simultaneous, just as an information. And you can have this kind of power, I mean, time-wise. With the time, you can just say, okay, I would like to have this power ratio in the two beams. In my CEDA, this looks a bit weird. You will ask me why this. Now, if you add these two together, and the sum of these two, and then you look a bit, oh, this looks like the skyline of the city of Stuttgart, actually. That's interesting, of course. But at the end of the day, you tell me, oh, but Marwan, you have a 60-second time scale. That's not fast enough. Yes, but we can do it also faster if you want. If I can shift, I can do it that short, the whole skyline, but I can do it also that short. And then if you zoom in, you have exactly the same. And if you look now to how you can make this, this is basically the skyline where you can visit the surrounding. If you take a car, you will need to go at the speed of 2,700,000 kilometers per hour, which is basically impossible. Yes, so to conclude my talk, I just want to finish with just this slide to show you how is the development of ultrafast lasers today within the years. You see all the lab results. Here the 10 kilowatt demonstrated with the coherent combining. Here our result on the multipass. But you see also the industrial lasers. Nowadays you can buy a kilowatt. And if you see that it follows a kind of linear, I mean, of course, here it's logarithmic in power-wise, but one can say we expect a 7 kilowatt ultra-fast laser commercially available in 2 years. It's a dream, but okay. Thank you very much. That's it for me.
Very much. Any question for him? I have a question. Yeah. You spoke about doping for considering ultra-fast pulses after that. What about co-doping to close rare earth ions to enlarge the spectrum and then to shorten the...
Yeah, we did not try this, but this can be at the cost of thermal conductivity then, sometimes. That's why it's a compromise. You can maybe, there have been also what is called ytterbium lutetium sesquioxide, I mean scandium lutetium oxide as a host, where they were broadening, but not with the dopant, with just the host, actually. That's it.
Any other questions for Marwan? No? I have another one.
Yes.
When you spoke about putting your thin discs in the middle of two... Sorry. When you spoke about putting your thin discs in the mirror of two diamonds, yes. What about the losses? What about, is no problem?
Very good question. I will just come back to this. Yes, here. Yeah, that's a very good question. That's what I said. There are a lot of challenges. The losses, the best diamond that you can find today have, let's say, quite low losses, which can be still acceptable. I mean, for what will be challenging is, of course, the surface quality, to polish this properly, and the coating that you will apply then between the different interfaces. That's why I said, this is just the beginning of the story. We demonstrated this for titanium sapphire because we wanted also to scale the average power of TISA. But we have seen also the challenges in the material itself, or in the process, let's say. It's not still well established like for the standard approach. But we believe a lot on this, actually. You can imagine that you can pump 10 times harder. This is what it means. So you can make very compact, high-power lasers.
Okay. So let's thank the speaker again and go to the...
Thank you very much.